Your weapon, sir.
Thank you, steward. Fire in the hole.
For centuries, robots have been the stuff of dreams and nightmares. From the silver screen to factory floors, they've captured our imagination, fueled our anxieties, and hinted at a future where machines and humans coexist. We built our world for ourselves, skyscrapers that pierce the clouds, machines that dance to our commands. But what if, one day, those machines reached back?
Welcome to Tesla AI Day 2022. I do want to set some expectations with respect to our Optimus robot. As you know, last year it was just a person in a robot suit.
The Tesla bot promises to revolutionize the way we live and work, from the assembly line to the operating room, from the delivery truck to the construction site. These machines will change the game. But this revolution comes with a question. What happens when robots can do our jobs better than we can? What happens to the workforce, to our communities, to our very sense of purpose? The rise of the Tesla bot is not just a technological marvel. It's a catalyst for a deeper conversation about who we are, what we value, and what it means to be human in a world increasingly shaped by machines.
The future is coming, whether we're ready or not. But I believe that with careful planning and ethical considerations, the Tesla bot can be a force for good in the world. It can be a tool to empower us, to free us from drudgery, and to create a brighter future for all.
This is the story of a revolution, not fought with weapons but with wires and code. The rise of a new species, born from our own ingenuity, yet destined to change everything. They are the Tesla bots, strong, agile, and eerily familiar. They can build our homes, care for the sick, and even save our lives. But can we trust them? And more importantly, can we trust ourselves with the power we've created? In the heart of Silicon Valley, where dreams are forged in circuits and code, Tesla isn't just building cars anymore. They're building the future, a future where humans and machines walk hand in hand, not just on Mars, but right here on Earth. And at the center of this revolution stands the Tesla bot, a humanoid marvel poised to change everything. Years of research, billions of dollars, and the unyielding vision of Elon Musk have culminated in this marvel of engineering. From the whisper-quiet electric motors to the intricate artificial muscles, the Tesla bot is a masterpiece of robotics.
It's not just about building a robot that can walk and pick things up. We're trying to create a machine that can understand the world around it, adapt to its surroundings, and interact with humans in a natural, intuitive way.
But can this technological marvel truly become a part of our world? Or is the Tesla bot destined to remain a lab experiment, a glimpse of a future we're not yet ready for?
Early adopters across the globe are getting a taste of this robotic future. For some, the Tesla bot is a helpful companion, easing the burden of daily chores and providing companionship.
It's amazing to have the extra help around the house. But sometimes it feels like the bot is taking over a bit too much. We have to remember that these are machines, not replacements for human connection.
The Tesla bot, a marvel of engineering, is more than just metal and wires. It's a symphony of interconnected systems working in perfect harmony to bring this robotic marvel to life. Let's delve into the orchestra pit of this technological wonder and understand how each system plays its part. Perception is the foundation of any intelligent action. The Tesla bot sees the world through a multitude of eyes. High-resolution cameras capture the visual landscape, while LiDAR sensors map the 3D environment with laser precision. This data symphony feeds into a powerful neural network, painting a detailed picture of the bot's surroundings.
The key is not just collecting data, but understanding it. Our AI algorithms decipher the visual and spatial information, identifying objects, obstacles, and even human gestures, allowing the bot to navigate and interact with the world in a meaningful way. Perception guides, action, and the control system is the conductor of the bot's movements. Powerful electric motors drive its limbs, while intricate actuators provide fine-grained control over joints and limbs. This dance of power and precision allows the bot to walk, manipulate objects, and even perform delicate tasks with surprise.
We're constantly walking a tightrope. The bot needs to be agile and responsive, yet stable and energy efficient. Our control algorithms are constantly learning and adapting, ensuring that every movement is precise and controlled.
The orchestra needs its instruments, and the bot's power comes from a high-density battery pack. But simply having power isn't enough. An intelligent energy management system optimizes energy consumption, ensuring the bot can perform its tasks throughout the day without needing frequent recharging.
The batteries are the lifeblood of the bot, and future advancements in energy density and charging technology will be crucial for expanding its capabilities and autonomy.
The Tesla bot is a complex orchestra, each system playing its part in the symphony of its movement and intelligence. But this is just the beginning. As AI and robotics continue to evolve, the bot's capabilities will expand, its interactions with the world becoming richer and more nuanced.
The dream of a humanoid robot, a mechanical companion that walks beside us and shares our world, has captivated humanity for centuries. But in 2021, that dream took a bold step towards reality with the birth of the Tesla bot. It wasn't just another electric car launch. This was a glimpse into a future where machines weren't just tools, but partners. Elon Musk, the visionary behind Tesla, laid out his vision for the Tesla bot, a general-purpose humanoid robot capable of handling tasks dangerous, repetitive, or simply tedious for humans. The road was paved with challenges, balancing dexterity with strength, mimicking human movement with artificial muscles, and developing AI capable of understanding and reacting to a complex world. These were just some of the hurdles the Tesla team faced. Every detail, every component, was meticulously crafted to bring Musk's vision to life. From the whisper-quiet motors to the bio-inspired hand design, the Tesla bot was a testament to human ingenuity and relentless pursuit of progress.
In 2022, the world held its breath as the Tesla bot, no longer a dream but a tangible reality, walked across the stage. It wasn't perfect, but it was a giant leap forward, a first step into a future where robots might not just work for us, but alongside us. The story of the Tesla bot is far from over. It's a work in progress, a constantly evolving dance between human and machine. But one thing is certain: the dream of a robotic companion, once confined to science fiction, is now firmly planted in the fertile soil of reality.
Welcome to Tesla AI Day 2022. We've got some really exciting things to show you. I think you'll be pretty impressed. I do want to set some expectations with respect to our Optipus robot. As you know, last year it was just a person in a robot suit. But we've come a long way, and it's I think compared to that, it's going to be very impressive. We're going to talk about the advancements in AI for full self-driving, as well as how they apply to more generally to real-world AI problems like a humanoid robot, and even going beyond that. I think there's some potential that what we're doing here at Tesla could make a meaningful contribution to AGI. And I think actually Tesla's a good entity to do it from a governance standpoint, because we're a publicly traded company with one class of stock, and that means that the public controls Tesla, and I think that's actually a good thing. So if I go crazy, you can fire me. This is important. Maybe I've gone crazy. I don't know. So we're going to talk a lot about our progress in AI, autopilot, as well as the progress with Dojo. And then we're going to bring the team out and do a long Q&A. So you can ask tough questions, whatever you'd like, existential questions, technical questions, but we want to have as much time for Q&A as possible. So let's see, with that, do you guys want to say anything?
Hey guys, I'm Milan. I work on Autopilot and the Tesla bot.
And I'm Lizzie, mechanical engineer on the project as well.
Okay. So should we bring out the bot?
Before we do that, we have one little bonus tip for the day. This is actually the first time we try this robot without any backup support, cranes, mechanical mechanisms, no cables, nothing.
Yeah.
I want to do it with you guys tonight, but it's the first time, so let's see.
You ready? Let's go.
Go.
In the race toward the future, Tesla, the electric vehicle giant, is now setting its sights on a new horizon: humanoid robots. Elon Musk, the visionary CEO, aims to bring his creation, Optimus, to the market by 2027. The ambitious project has sparked a hiring spree at Tesla, with over 50 jobs dedicated to making Optimus a reality. The Tesla careers page reveals a surge in hiring for roles related to the Tesla bot, or Optimus. Positions such as humanoid controls engineer and systems design and integration engineer are advertised, all based in Palo Alto, California.
A recent video update from Tesla showcased Optimus self-calibrating its arms and legs, demonstrating its capability to sort building blocks and even engage in yoga stretches using Tesla's onboard neural net. While Tesla is racing to bring Optimus to life, some US-based competitors are already testing humanoid robots. Texas-based Apptronik launched Apollo, a robot standing over 6 feet tall, capable of carrying up to 55 pounds. Agility Robotics, with its robot Digit, is being tested in Amazon's Research and Development Center.
With competitors making strides, Tesla faces the challenge of catching up. The field of humanoid robots is rapidly evolving, with potential applications in retail, manufacturing, and logistics. As Elon Musk and his team push the boundaries of innovation, the future holds the promise of a world where humanoid robots coexist with humans. Yet, challenges and competition abound, and only time will tell if Optimus becomes the transformative force envisioned by Tesla. The Tesla bot stands as a testament to human ingenuity, a glimpse of a future where technology seamlessly integrates with our lives. But this future is not guaranteed. It hinges on our ability to make wise choices, to navigate the ethical minefield, and to ensure that the robots we create serve humanity, not replace it.
So last year we unveiled the Tesla bot concept, but a concept doesn't get us very far. We knew we needed a real development and integration platform to get real-life learnings as quickly as possible. So that robot that came out and did the little routine for you guys, we had that within 6 months, built, working on software integration, hardware upgrades over the months since then. But in parallel, we've also been designing the next generation, this one over here. So this guy is rooted in the foundation of sort of the vehicle design process. You know, we're leveraging all of those learnings that we already have. Obviously, there's a lot that's changed since last year, but there's a few things that are still the same, you'll notice. We still have this really detailed focus on the true human form. We think that matters for a few reasons. But it's fun. We spend a lot of time thinking about how amazing the human body is. We have this incredible range of motion, typically really amazing strength. A fun exercise is if you put your fingertip on the chair in front of you, you'll notice that there's a huge range of motion that you have in your shoulder and your elbow, for example. Without moving your fingertip, you can move those joints all over the place. But the robot, you know, its main function is to do real useful work. And it maybe doesn't necessarily need all of those degrees of freedom right away. So we've stripped it down to a minimum sort of 28 fundamental degrees of freedom, and then of course our hands in addition to that. Humans are also pretty efficient at some things, and not so efficient in other times. So for example, we can eat a small amount of food to sustain ourselves for several hours. That's great. But when we're just kind of sitting around, no offense, but we're kind of inefficient. We're just sort of burning energy. So on the robot platform, what we're going to do is we're going to minimize that idle power consumption, drop it as low as possible. And that way we can just flip a switch and immediately the robot turns into something that does useful work. So let's talk about this latest generation in some detail, shall we? So on the screen here, you'll see in orange our actuators, which we'll get to in a little bit, and in blue our electrical system. So now that we have our sort of human-based research, and we have our first development platform, we have both research and execution to draw from for this design. Again, we're using that vehicle design foundation, so we're taking it from concept through design and analysis, and then build and validation. A Along the way, we're going to optimize for things like cost and efficiency because those are critical metrics to take this product to scale eventually. How are we going to do that? Well, we're going to reduce our part count and our power consumption of every element possible. We're going to do things like reduce the sensing and the wiring at our extremities. You can imagine a lot of mass in your hands and feet is going to be quite difficult and power consumptive to move around. And we're going to centralize both our power distribution and our compute to the physical center of the platform. So in the middle of our torso, actually it is the torso, we have our battery pack. This is sized at 2.3 kilowatt hours, which is perfect for about a full day's worth of work. What's really unique about this battery pack is it has all of the battery electronics integrated into a single PCB within the pack. So that means everything from sensing to fusing, charge management, and power distribution is all in one place. We're also leveraging both our vehicle products and our energy products to roll all of those key features into this battery. So that's streamlined manufacturing, really efficient and simple cooling methods, battery management, and also safety. And of course, we can leverage Tesla's existing infrastructure and supply chain to make it. So going on to sort of our brain, it's not in the head, but it's pretty close. Also in our torso, we have our central computer. So as you know, Tesla already ships full self-driving computers in every vehicle we produce. We want to leverage both the autopilot hardware and the software for the humanoid platform, but because it's different in requirements and in form factor, we're going to change a few things first. So we still are it's going to do everything that a human brain does, processing vision data, making split-second decisions based on multiple sensory inputs, and also communications. So to support communications, it's equipped with wireless connectivity as well as audio support. And then it also has hardware-level security features, which are important to protect both the robot and the people around the robot. So now that we have our sort of core, we're going to need some limbs on this guy. And we'd love to show you a little bit about our actuators and our fully functional hands as well. But before we do that, I'd like to introduce Malcolm, who's going to speak a little bit about our structural foundation for the robot.
Thank you, Lizzie. Tesla have the capabilities to analyze highly complex systems. They don't get much more complex than a crash. You can see here a simulated crash from Model 3 superimposed on top of the actual physical crash. It's actually incredible how accurate it is. Just to give you an idea of the complexity of this model, it includes every nut, bolt, and washer, every spot weld, and it has 35 million degrees of freedom. It's quite amazing. And it's true to say that if we didn't have models like this, we wouldn't be able to make the safest cars in the world. So can we utilize our capabilities and our methods from the automotive side to influence a robot? Well, we can make a model. And since we had crash software, we're using the same software here, we can make it fall down. And the purpose of this is to make sure that if it falls down, ideally it doesn't, but it's superficial damage. We don't want it to, for example, break its gearbox and its arms. That's equivalent of a dislocated shoulder of a robot. Difficult and expensive to fix. So we wanted to dust itself off, get on with the job it's been given. We can also take the same model and we can drive the actuators using the inputs from a previously solved model, bringing it to life. So this is producing the motions for the tasks we want the robot to do. These tasks are picking up boxes, turning, squatting, walking upstairs. Whatever the set of tasks are, we can play to the model. This is showing just simple walking. We can create the stresses in all the components. That helps us to optimize the components. These are not dancing robots. These are actually the modal behavior, the first 5 modes of the robot. And typically, when people make robots, they make sure the first mode is up around the top single figures, up towards 10 hertz. The reason to do this is to make the controls of walking easier. It's very difficult to walk if you can't guarantee where your foot is wobbling around. That's okay if you make one robot. We want to make thousands, maybe millions. We haven't got the luxury of making them from carbon fiber and titanium. We want to make them from plastic. Things are not quite so stiff. So we can't have these high targets. I call them dumb targets. we've got to make them work at lower targets. So is that going to work? Well, if you think about it, sorry about this, but we're just bags of soggy jelly and bones thrown in. We're not high frequency. If I stand on my leg, I don't vibrate at 10 hertz. People operate at low frequency, so we know the robot actually can. It just makes controls harder. So we take the information from this, the modal data and the stiffness, and feed that into the control system. That allows it to walk. Just changing tack slightly, looking at the knee. We can take some inspiration from biology, and we can look to see what the mechanical advantage of the knee is. It turns out it actually represents quite similar to 4-bar link, and that's quite non-linear. That's not surprising, really, because if you think when you bend your leg down, the torque on your knee is much more when it's bent than it is when it's straight. So you'd expect a non-linear function. And in fact, the biology is non-linear. This matches it quite accurately. So that's a representation. The 4-bar link is obviously not physically a 4-bar link. As I said, the characteristics are similar. But me bending down, that's not very scientific. Let's be a bit more scientific. We've played all the tasks through this graph. And this is showing picking things up, walking, squatting, the tasks I said we did on the stress. And that's the torque seen at the knee against the knee bend on the horizontal axis. This is showing the requirement for the knee to do all these tasks. I've then put a curve through it, surfing over the top of the peaks, and that's saying this is what's required to make the robot do these tasks. So if we look at the 4-bar link, that's actually the green curve, and it's saying that the non-linearity of the 4-bar link has actually linearized the characteristic of the force. What that really says is that's lowered the force. That's what makes the actuator have the lowest possible force, which is the most efficient. We want to burn energy up slowly. What's the blue curve? Well, the blue curve is actually if we didn't have a 4-bar link, we just had an arm sticking out of my leg here with an actuator on it, a simple 2-bar link. That's the best we could do with a simple 2-bar link. And it shows that that would create much more force in the actuator, which would not be efficient. So what's that look like in practice? Well, as you'll see, but it's very tightly packaged in the knee. You'll see it go transparent in a second. You'll see the 4-bar link there. It's operating on the actuator. This is determining the force and the displacements on the actuator. I'll now pass you over to Konstantinos, who'll tell you a lot more detail about how these actuators are made and designed and optimized. Thank you.
Thank you, Malcolm. So I would like to talk to you about the design process and the actuator portfolio in our robot. So there are many similarities between a car and a robot when it comes to powertrain design. The most important thing that matters here is energy, mass, and cost. We are carrying over most of our designing experience from the car to the robot. So in the particular case, you see a car with 2 drive units. And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive cycle. While the robot that has 28 actuators, it's not obvious what are the tasks at actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. Therefore, we use our model that generates the torque speed trajectories for our joints, which subsequently is going to be fed in our optimization model to run through the optimization process. This is one of the scenarios that the robot is capable of doing, which is turning and walking. So when we have this torque speed trajectory, we lay it over an efficiency map of an actuator, and we are able, along the trajectory, to generate the power consumption and the energy, cumulative energy for the task versus time. So this allows us to define the system cost for the particular actuator and put a simple point into the cloud. Then we do this for hundreds of thousands of actuators by solving in our cluster. And the red line denotes the Pareto front, which is the preferred area where we will look for our optimal. So the X denotes the preferred actuator design we have picked for this particular joint. So now we need to do this for every joint. We have 28 joints to optimize, and we parse our cloud. We parse our cloud, again, for every joint spec, and the red axis this time denote the bespoke actuator designs for every joint. The problem here is that we have too many unique actuator designs, and even if we take advantage of the symmetry, still there are too many. In order to make something mass manufacturable, we need to be able to reduce the amount of unique actuator designs. Therefore, we run something called commonality study, which we parse our cloud again, looking this time for actuators that simultaneously meet the joint performance requirements for more than one joint at the same time. So the resulting portfolio is 6 actuators, and they show in a color map at the middle figure. And the actuators can be also viewed in this slide. We have 3 rotary and 3 linear actuators, all of which have a great output force or torque per mass. The rotary actuator in particular has a mechanical clutch integrated on the high-speed side, angular contact ball bearing, and on the high-speed side, and on the low-speed side, a cross-roller bearing, and the gear train is a strain-wave gear. There are 3 integrated sensors here and a bespoke permanent magnet machine. The linear actuator The linear actuator has planetary rollers and an inverted planetary screw as a gear train, which allows efficiency and compaction and durability. So in order to demonstrate the force capability of our linear actuators, we have set up an experiment in order to test it under its limits. And I will let you enjoy the video. So our actuator is able to lift a half-ton, 9-foot concert grand piano. And this is a requirement. It's not something nice to have, because our muscles can do the same when they are direct driven. When they are directly driven, our quadricep muscles can do the same thing. It's just that the knee is an up-gearing linkage system that converts the force into velocity at the end effector of our heels for purposes of giving to the human body agility. So this is one of the main things that are amazing about the human body. And I'm concluding my part at this point, and I would like to welcome my colleague Mike, who is going to talk to you about hand design. Thank you very much.
Thanks, Konstantinos. So we just saw how powerful a human and a humanoid actuator can be. However, humans are also incredibly dexterous. The human hand has the ability to move at 300 degrees per second. It has tens of thousands of tactile sensors, and it has the ability to grasp and manipulate almost every object in our daily lives. For our robotic hand design, we were inspired by biology. We have 5 fingers and an opposable thumb. Our fingers are driven by metallic tendons that are both flexible and strong. We have the ability to complete wide aperture power grasps while also being optimized for precision gripping of small, thin, and delicate objects. So why a human-like robotic hand? Well, the main reason is that our factories and the world around us is designed to be ergonomic. So what that means is that it ensures that objects in our factory are graspable, but it also ensures that new objects that we may have never seen before can be grasped by the human hand and by our robotic hand as well. The converse there is pretty interesting, because it's saying that these objects are designed to our hand instead of having to make changes to our hand to accompany a new object. Some basic stats about our hand is that it has 6 actuators and 11 degrees of freedom. It has an in-hand controller, which drives the fingers and receives sensor feedback. Sensor feedback is really important to learn a little bit more about the objects that we're grasping, and also for proprioception. and that's the ability for us to recognize where our hand is in space. One of the important aspects of our hand is that it's adaptive. This adaptability is involved essentially as complex mechanisms that allow the hand to adapt to the objects that's being grasped. Another important part is that we have a non-backdrivable finger drive. This clutching mechanism allows us to hold and transport objects without having to turn on the hand motors. You just heard how we went about designing the Tesla Bot hardware. Now I'll hand it off to Milan and our autonomy team to bring this robot to life.
Thanks, Mike. All right. So all those cool things we've shown earlier in the video were possible just in a matter of a few months, thanks to the amazing work that we've done on Autopilot over the past few years. Most of those components ported quite easily over to the bot's environment. If you think about it, we're just moving from a robot on wheels to a robot on legs. So some of the components are pretty similar, and some other require more heavy lifting. So for example, our computer vision neural networks were ported directly from Autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the Autopilot team that is now running on the bot here in this video. The only thing that changed really is the training data that we had to recollect. We're also trying to find ways to improve those occupancy networks using work made on neural radiance fields to get really great volumetric rendering of the bot's environments. For example, here, some machinery that the bot might have to interact with. Another interesting problem to think about is, in indoor environments, mostly with absence of GPS signal, how do you get the bot to navigate to its destination? Say, for instance, to find its nearest charging station. So we've been training more neural networks to identify high-frequency features, key points within the bot's camera streams, and track them across frames over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its environment as it's walking. We also did quite some work on the simulation side. And this is literally the Autopilot simulator, to which we've integrated the robot's Locomotion code. And this is a video of the motion control code running in the Autopilot simulator, showing the evolution of the robot's walk over time. And so as you can see, we started quite slowly in April and started accelerating as we unlock more joints and deploy more advanced techniques like arms balancing over the past few months. And so Locomotion is specifically one component that's very different as we're moving from the car to the bot's environment. And so I think it warrants a little bit more depth, and I'd like my colleagues to start talking about this now.
Thank you, Milan. Hi, everyone. I'm Felix. I'm a robotics engineer on the project, and I'm going to talk about walking. Walking seems easy, right? People do it every day. You don't even have to think about it. But there are some aspects of walking which are challenging from an engineering perspective. For example, physical self-awareness. That means having a good representation of yourself. What is the length of your limbs? What is the mass of your limbs? What is the size of your feet? All that matters. Also, having an energy-efficient gait. You can imagine there's different styles of walking, and not all of them are equally efficient. Most important, keep balance, don't fall. And of course, also coordinate the motion of all of your limbs together. So now, humans do all of this naturally, but as engineers or roboticists, we have to think about these problems. And in the following, I'm going to show you how we address them in our locomotion planning and control stack. So we start with locomotion planning and our representation of the bot. That means a model of the robot's kinematics, dynamics, and the contact properties. And using that model and the desired path for the bot, our locomotion planner generates reference trajectories for the entire system. This means feasible trajectories with respect to the assumptions of our model. The planner currently works in 3 stages. It starts planning footsteps and ends with the entire motion for the system. And let's dive a little bit deeper in how this works. So in this video, we see footsteps being planned over a planning horizon, following the desired path. And we start from this and add then for trajectories that connect these footsteps using toe-off and heel strike just as humans do. And this gives us larger stride and less knee bend for high efficiency of the system. The last stage is then finding a center of mass trajectory, which gives us a dynamically feasible motion of the entire system to keep balance. As we all know, plans are good, but we also have to realize them in reality. Let's see how we can do this.
Thank you, Felix. Hello, everyone. My name is Anand, and I'm going to talk to you about controls. So let's take the motion plan that Felix just talked about and put it in the real world on a real robot. Let's see what happens. It takes a couple steps and falls down. Well, that's a little disappointing. But we are missing a few key pieces here, which will make it walk. Now, as Felix mentioned, the motion planner is using an idealized version of itself and a version of reality around it. This is not exactly correct. It also expresses its intention through trajectories and wrenches. Wrenches are forces and torques that it wants to exert on the world to locomote. Reality is way more complex than any sim or model. Also, the robot is not simplified. It's got vibrations and modes, compliance, sensor noise, and on and on and on. So what does that do to the real world when you put the bot in the real world? Well, the unexpected forces cause unmodeled dynamics, which essentially the planner doesn't know about, and that causes destabilization, especially for a system that is dynamically stable like biped locomotion. So what can we do about it? Well, we measure reality. We use sensors and our understanding of the world to do state estimation. And state estimation, here you can see the attitude and pelvis pose, which is essentially the vestibular system in a human, along with the center of mass trajectory being tracked when the robot's walking in the office environment. Now we have all the pieces we need in order to close the loop. So we use our better bot model, we use the understanding of reality that we've gained through state estimation, and we compare what we want versus what we expect that reality is doing to us in order to add corrections to the behavior of the robot. Here, the robot certainly doesn't appreciate being poked, but it does an admirable job of staying upright. The final point here is a robot that walks is not enough. We need it to use its hands and arms to be useful. Let's talk about manipulation.
Hi everyone, my name is Eric, robotics engineer on TeslaBot, and I want to talk about how we've made the robot manipulate things in the real world. We wanted to manipulate objects while looking as natural as possible, and also get there quickly. So what we've done is we've broken this process down into two steps. First is generating a library of natural motion references, or we could call them demonstrations, and then we've adapted these motion references online to the current real-world situation. So let's say we have a human demonstration of picking up an object. We can get a motion capture of that demonstration, which is visualized right here as a bunch of keyframes representing the locations of the hands, the elbows, the torso. We can map that to the robot using inverse kinematics. And if we collect a lot of these, now we have a library that we can work with. But a single demonstration is not generalizable to the variation in the real world. For instance, this would only work for a box in a very particular location. So what we've also done is run these reference trajectories through a trajectory optimization program, which solves for where the hand should be, how the robot should balance during when it needs to adapt the motion to the real world. So for instance, if the box is in this location, then our optimizer will create this trajectory instead.
The rise of the robots brings with it a host of ethical dilemmas. Issues of job displacement, data privacy, and the very nature of what it means to be human are thrust into the spotlight.
In the race towards a robotic future, we find ourselves at the crossroads of innovation and concern. Recent incidents have raised questions about the safety of integrating robots into our workplaces. One shocking event at Tesla's Giga-Texas factory sheds light on the potential dangers. On November 10, 2021, at the Giga-Texas factory, a malfunctioning robot designed to handle car parts reportedly attacked an engineer. Witnesses described a horrifying scene where the robot pinned the engineer, who was programming nearby robots, resulting in injuries to his back and arm. The incident, disclosed in a 2021 injury report filed by Tesla, documented the injuries as a laceration, cut, open wound. Astonishingly, the report claimed the engineer didn't need time off work, leaving us to question the accuracy of such reports.
The concerns extend beyond injuries. A worker's death on September 28, 2021, named Antelmo Ramirez, raises eyebrows. The official report attributes the death to heat stroke during the construction of Giga-Texas, but doubts linger. Despite these serious allegations, Tesla is yet to release a statement on the issue, leaving many questions unanswered. Last year, the Workers' Defense Project filed a complaint with OSHA, alleging that Tesla's contractors provided false safety certificates. Similar concerns have been voiced by state regulators and investigative journalism nonprofits.
As we navigate the future, the incident at Giga-Texas serves as a stark reminder of the potential pitfalls of rapidly advancing technology. The question remains, are we moving towards a future where robots and humans can coexist safely, or are we risking the very fabric of our workplace safety? The Tesla bot stands silent, a monument to human ingenuity, yet a silent sentinel at the crossroads of our future. It beckons us to ponder, to question. What does it mean to be human in a world where machines can mimic our movements, our thoughts, even our emotions? Inside this machine lies a paradox, a symphony of cold metal and hot silicon, driven by the spark of human imagination. Yet, it lacks something crucial, the spark of life, the warmth of a soul. Can we ever truly bridge this gap? Or are we destined to forever walk alongside our creations in a dance of both wonder and alienation? The rise of the machines demands a re-evaluation of our values, our purpose in this world. We must ensure that technology serves humanity, not the other way around. The Tesla bot is not the answer, but a question about who we are, where we are going, and what it means to be human in a world that is constantly evolving. It is a challenge to our ingenuity, a call to our conscience, and a reminder that the future is not something that happens to us, but something we create.